wants to know dynamic behavior of structures, but we don't have enough time to cover the whole course. So I will give you a brief introduction on dynamic behavior of structures under different loading conditions and different systems. So you have a general concept on dynamic stability. Okay, dynamic stability in Chinese is 动力稳定性. I have sent this part of the notes to Professor Tang, and I'm not sure if he has time to distribute it. If not, you just follow the screen, and Professor Tang will send you the notes afterward. Many failures of engineering structures under either static or dynamic loadings have been attributed to structural stability or instability. 结构失稳 in which large deformations of the structures are observed. In the study of stability of structures, it is the nature of the loading that characterize the nature of the problem to be solved. Okay, so depending on the loading, we have different problems. For example, the loading can be static, it can be deterministic, or random. We will explain this in detail in a moment. Problems of parametric resonance. Parametric comes from parameter. 参数共振 arise naturally in studies of dynamic stability of a class of elastic systems. For example, we can have column under compressive axial load, and we studied in mechanics, if you have a column if you consider a column under axial load, when the load is equal to the Euler buckling load, the structure will buckle. Okay, now what happens if the load is dynamic instead of a static load? Then we have a dynamic stability. These systems ordinarily exhibit a bifurcational form. We will explain bifurcation later, 分场 of instability under applied static loads. The external applied loads appear in the equation of motion in the form of coefficients or parameters. Okay. So far we studied the system under external loading equal to Ft. Okay, so in this case, the loading appears on the right-hand side of the differential equation, of the equation of motion. Now, if the loading appears as the parameter, for example, k minus ft x, okay, now if the loading appears in the equation of motion as a coefficient or as a parameter, then we have parametric system. As a result, when the loading are dynamic or time-dependent, the system are called a parametrically excited system. Okay, because the loading appears as a parameter, and the instability is referred as parametric instability or parametric resonance. Okay, we will explain this in more details. Parametric instability problems also occur in the analysis of steady-state motion of nonlinear systems. And so far, we only studied deterministic loadings. So that means the loading is a known function of time t, ft, which can be either a harmonic function. Harmonic function means 谐波. So it's a sine function or a cosine function, or a superimposition of several harmonic functions. So it can be a periodic function, 或者是一个周期函数. Such as the excitations arising from unbalanced masses in rotating machinery. In engineering applications, loadings are quite often random forces, 随机. For example, those from earthquakes, wind load, and ocean waves in onshore and offshore structure, which can be described satisfactorily only in probabilistic terms. Okay, so these are the 随机力. That's what we are going to study in the second part of this course. Under the action of such loadings, the parameters that describe the motion of a structure will fluctuate in a stochastic manner. Stochastic is similar to random, but there's some difference. We will not go into details, but you just consider it's random. As a result, the response of the structure is governed by stochastic differential equations. In which the parameters or coefficients are stochastic processes. Okay, there are also cases, situations where loadings on a system contain both periodic components and stochastic fluctuations. An example of such a system is uncoupled flapping motion of rotor blades in forward flight under the effect of atmospheric turbulence. So in this case, we have periodic components, and then on top of the periodic components, you have stochastic random fluctuation. Okay, so the loading contains both periodic components and the stochastic fluctuations. For ordinary or mean resonance, that's what we studied in chapter 2 and chapter 3. The excitations appear as forcing term on the right-hand side. Okay, that's the equation I wrote here. The forcing appears on the right-hand side of the equation. Resonance occurs when the excitation frequency coincides or is the same as the natural frequency of the system. In such case, the response amplitude will grow linearly. In the absence of damping, if there's no damping. Parametric resonance is very different. Parametric resonance is characterized by exponential growth or build-up of the response amplitudes even in the presence of damping. Even when we have damping, the amplitude will grow exponentially. Furthermore, parametric resonance occurs not only at a single excitation frequency, but over several bands of excitation frequencies. Okay, so that's the difference. We will study this in detail later today. As a result, parametric instability is more dangerous than that due to ordinary or mean resonance. Okay, depending on the characteristics of structures, depending what kind of structures you have, and what kind of loading you have. It can be static, deterministic, or stochastic, random. The stability problems of structures can be classified in the following figure. Okay, so if we have static loading, then we have velocity independent or velocity dependent systems. Okay, we are familiar with this first case. It's Euler buckling. Here you have a column. It's a cantilever, and it's subjected to actual load. And in this case, the load is always vertical. Okay? And so when PF is equal to the Euler buckling load, we have buckling. Okay? So in this case, the load is vertical. It has a fixed direction. And the system is non-oscillatory, conservative system. Now for the buckling problem, if the load is not always vertical, but follows the deformation of the column. So in this case, it's tangent to the column at the tip. Okay, so the load always changes. The direction of the load changes with the deformation. So if you deform to this, then the load changes to this direction. Okay? So this load is called follower force. You know, follow means, right? It follows the deformation of the column. Okay, so this is called a follower force. It follows the deformation of the system, of the the column, and this becomes a non-conservative system. And we will define conservative and non-conservative system in a moment. And if it depends on velocity, so for example, you have pipes conveying fluid. Okay, so you have water flowing inside the pipe. Okay, so the flow velocity is u. Then you would have different system depending on the support. If you have both ends rigidly supported, okay, so we have a clamped support at one end and a pin support at the other end, then we have a gyroscopic conservative system. A gyroscope is 陀螺. And if one end is free and it can move freely, then it becomes a non-conservative system. Okay, now we can also study when we have time-dependent loading or dynamic loading. And you can have periodic loading or stochastic loading. Okay? Now, if you apply this loading to the systems we just discussed, then you have a gyroscopic or non-gyroscopic systems. Okay, so for example, you can have U plus U1T. So in this case, you can have U0. Okay, so that's UT. So you have a constant flow velocity. Okay, and then on top of it, you can have fluctuations. Okay, so in this case, we would have the load apply to the system. Okay, so now first let's look at the conservative systems. A conservative system, a potential energy function can be determined in which U is the displacement field and mu is the loading parameter. Okay, so you can find the potential energy of the system in terms of the displacement and the loading. The minimum potential energy law, which follows Lagrange's theorem, states that the system is in a state of stable equilibrium if and only if the value of the potential energy is a relative minimum. The word relative is used because there may be other minima nearby, separated from this minimum by small hills as illustrated here. Okay, so here we have a relative minimum. Okay, so if you give the system a perturbation means 扰动. So if you push it a little bit, it will still come back. Okay, it will move around and then come back to the stable position. But if you push it too much, it will fall and then come to this relative minimum. Okay, so that's stable. And this position is also stable. That means when you give it a small perturbation or disturbance, it will come back to the equilibrium position. And this is unstable. If you give it a small perturbation, it will fall off the heel. And this is a critical point. Okay, so now let's look at a simple example to illustrate stability under static load. Okay, so this is a simple model of a cantilever column under a vertical load P. Okay, and we can use a simpler model, a rigid bar, and a torsional spring. To model this, and that's the name for this structure. It's called Roda's column. And this was developed by a professor from my university, University of Waterloo. And it's very good in using a simple model to model a more complex structure. And you can study this and get the essential behavior of a system. Okay, so we look at a rigid bar supported by a torsional spring, and it's pinned here. Okay, so the torsional spring models the clamped support. Okay, so when we apply a vertical load, and when P is larger than some P critical value, we will have buckling. Okay, so we impose a small rotation Q equal to theta. This is the generalized coordinate. And okay, so you give a small rotation theta. Then we have the potential energy. This is the potential energy of the spring, half kappa. Kappa is the spring stiffness of the spring, theta squared. Okay, so this is the potential energy in the torsional spring. And the minus PL1 minus cosine theta. L times 1 minus cosine theta is the displacement of the tip of the bar. Okay, so from here to here. Therefore, P times the displacement gives us the work done by the force P. Okay, so that gives us the potential energy. And for small amplitude of rotation, we use Taylor series. Cosine theta is 1 minus half theta squared. And so equation 1.1 can be approximated by this. Okay, so we have one variable, theta. And for equilibrium, the first order derivative of the potential energy is 0. Okay, so take first order derivative with respect to theta. We have theta times kappa minus PL equal to 0. We have two solutions for this equation. Either theta is equal to 0. When theta is 0, it's not interesting. Okay? So if P is not equal to kappa over L, the angle of rotation theta is always 0, which is the non-buckled configuration. It's the 0 configuration. When P is equal to kappa over L, so this term becomes 0. Then theta can be any non-zero values corresponding to the buckled configuration. And we can study whether this equilibrium position is stable or unstable by taking the second order derivative. The second order derivative is positive, then we have a minimum. If it's less than 0, then we have a maximum. If it's equal to 0, then we have a critical point. We don't know whether it's maximum or minimum. Okay, so when it's positive, when the second order derivative is positive, we have a minimum. Okay, so you can see if it's a minimum, it's stable. If it's a maximum, it's unstable. If it's 0, it's a critical point. Okay, so when P is less than K over L, that means this is positive. Okay, which means the potential energy is minimum at theta equal to 0, and the non-buckled configuration is stable. When P is equal to kappa over L, the second order derivative is 0. The equilibrium position is critical and the buckling occurs. When P is larger than kappa over L, the second order derivative is negative, implying that the non-buckling configuration is unstable. Okay, so we can plot something called a load rotation curve. Okay, so you apply a load. When the load is small, the 0 configuration is stable. So P is less than kappa over L. Now when P reaches the buckling load, kappa over L, then we have buckling. Okay, so this is the same as a cantilever column. When P equals the Euler buckling load, we have instability or buckling. Okay, so when the load is less than the Euler buckling load, this is stable. The 0 configuration is stable. When it reaches the critical load, then we have buckling. Okay, so there will be a theta. Okay, and this is the simple case for when we have this simple model. When we have the cantilever column, if you recall what we studied mechanics 材料力学。Suppose this is a delta. Okay, so we plot delta. Then it's 0 when it's less than the Euler buckling load. When it's larger than the Euler buckling load, then we have this. Okay, so this is P. And for a simple model, this is a horizontal straight line. When you have elastic column, then it's this. Okay, so this looks like a pitchfork. Okay, so and then this becomes unstable. This is stable. Okay, so mathematically this is also called pitchfork bifurcation. Bifurcation means 分叉. Okay, so it looks like a pitchfork. So you have one stable position, and then it bifurcates, 分叉. Okay, bifurcates at this point. And we have two pieces because delta can go this way. It can also buckle this way. Okay, so in this case, delta is positive. Here, delta is negative. Okay, so we would have a pitchfork bifurcation. Okay, so this is a conservative system. Now we study non-conservative system. A force is conservative if the work W done along the displacement of its point of application depends solely on the initial and the final position of this point. A force satisfying this condition is a conservative force. A force that does not satisfy this condition is non-conservative. So for example, gravity is conservative. Okay, you can drop the work done by the gravity depends only on the initial position and the final position. And it does not depend on, you may have a slope and then it runs from here to here. It only depends on the initial position and the final position. Does not depend on the path. Okay, so now if we have a force that is non-conservative, then the system is non-conservative. Okay, so for example, you have a follower force, or the follower force can be tangential to the whole column. Okay, we have pipes conveying fluids. Okay, you have a pipe with a fluid running through it. Okay, for different support conditions, you have different systems. Here, it's free at one end, it's supported but free here, and we have elastic support. You have elastic support along the whole pipe. Okay, now for non-conservative system, you can have a panel and with supersonic flow, or this is airplane. Okay. So in these cases, we have non-conservative systems. Okay, now let's look at a simple non-conservative system. In this case, we have a Rhodes column. It has two pieces. I think you did an assignment similar to this in assignment number one, right? So we have two rigid bars. It carries two lumped masses, M1 and M2, and we have two torsional springs, copper 1, copper 2, connecting the two links and the support. Okay, you did this in your assignment, and we can set up the equation, and we use two generalized coordinates: angle theta 1, theta 2, or you can use horizontal displacement Q1 and Q2. Okay, either one is fine. And you can relate theta 1, theta 2 with Q1 and Q2 using these relationships. Okay, so by considering the equilibrium of link BC and system ABC, we can set up the equations. I will skip this using D'Alembert's principle. Okay, so now if we look for a solution, Q1T, Q2T equal to Q1 hat, Q2 hat, e to the lambda t, and substitute into the equation of motion, we end up with this. Okay, so this is a system of two homogeneous algebraic equations. Okay, so for this to have non-zero solutions, the determinant of the coefficient matrix must be 0. Okay, so we pick up the coefficients and write the matrix, and the determinant must be 0. Okay, so then you expand the 2 by 2 determinant. You get an equation. It is a fourth order polynomial. Okay, but it can be treated as a quadratic equation in terms of lambda squared. And you can solve this to find the roots for lambda. Okay, so you have positive, negative here. Now if this term is negative, when you take square root, this becomes purely imaginary. Okay, so if this term is negative, square root of a negative number is imaginary. Now, if it is positive, if this term is positive, then we will have positive and negative. Okay, if this term is then we will have two real roots. One positive and one negative. Okay, so it is obvious that if all of the four roots given by this equation are not purely imaginary, they are one-pair complex roots with a positive real part. In order to have all purely imaginary roots, then this must be positive, and this term must be positive. Okay, then you have negative, and A2 is bigger than a square root of this. Okay, so that means we have negative. Okay. Okay, so which yields A2 is larger than 2 square root 80. Hence, the critical load is given by this. Okay, so this is the critical load. And then if you substitute into by the equations involving P, we find the critical load is given by this expression. Okay, so when P is less than P critical, all four roots are purely imaginary in this form, yielding a circulatory sinusoidal solution of the form 2.1 and for the equation 2.1, 2.2. Okay, so that means the solution is equal to something involving omega 1t sine omega 2t. Okay, so the solution will be in this form, and it's circulatory or oscillatory. Okay, now when P is larger than P critical, then we will have one pair of complex roots with positive real parts. Okay, so you have a real part. Then you will have e to the alpha t. Now because alpha is positive, then the solution will grow exponentially. Okay, so this will grow exponentially when P larger than P critical. Okay, so this is a dynamic buckling. Okay, so when P is less than P critical, you have sinusoidal solutions, oscillatory solutions. When P is larger than P critical, we have this term. And because of this term, the solution grows exponentially. Okay? So now in general, for a non-conservative system, we have an extra term. And remember, this is the system we have for conservative. And the extra term, mu bx, gives us the conservative system. Okay, and we know that M and K are symmetric. For non-conservative system, B is not symmetric in general. Now, if we apply modal analysis, we can diagonalize the mass matrix and stiffness matrix is using the modal matrix phi. Okay, we studied this in chapter 3 for multiple degrees of freedom system. And we assume that we are also able to diagonalize the damping matrix, but in general, we cannot diagonalize the matrix B. Okay, matrix B is called geometric stiffness matrix. It's different from the matrix K, which is the elastic stiffness matrix. Okay, so now because of this, we cannot diagonalize the B matrix. Okay, so you will have this extra term when we apply modal analysis. Okay, now if we look for a solution of this form, Qt equal to Q hat e to the lambda t, and substitute into the equation, you have this term. Okay, now to have non-trivial or non-zero solutions, the determinant of the coefficient matrix must be 0. And then we can solve this to find the roots. And this is our new characteristic equation. Okay, so now let's review what we studied in differential equations. If lambda is equal to alpha, okay, then the solution, we use Q, is equal to Qt then Qt is equal to e to the alpha t. Okay, so now if alpha is positive, the solution will grow exponentially. If alpha is less than 0, then it will decay exponentially. Okay, so now if we have a double root, then Q is there will be C here, so it's C0 plus C1T e to the lambda alpha t. Okay, so now if you have lambda equal to 0, 0, so this would grow exponentially depending on alpha. Okay, but if lambda is 0, 0, then we have C0 plus C1t. Okay, so it grows linearly. And if you have pure imaginary roots, then Q is A cosine omega t plus B sine omega t. Okay, now if you have alpha plus I omega, then Q is e to the alpha t, A cosine omega t plus B sine omega t. Okay, so we will take a short break, say 7 minutes, and please review this part. We will see what happens for our system if the roots change. Okay. Please come back at 9 o'clock.汤老师，
谢教授。
你好，你问问他们有没有学过那个随机过程？
好的。
应该概率统计、概率论、数体统计应该学过吧？
大学本科一般都学过概率。他们没有学过随机过程这样的。
OK。 Okay, let's continue. Give you something to think about. If you have a pipe, and we have water going through it. Okay, now if you increase the speed of flow, what happens? Okay, give you a few seconds to think about it, visualize in your mind. If you increase the flow velocity, what happens to the pipe? Okay, we have a pipe. It's clamped at one end and free at the other end. Okay, so when flow velocity is small, nothing happens. Okay, so the flow will just the water will just flow out of the pipe. When you increase V such that U is larger than critical velocity, then the pipe will start to vibrate. Okay, I will show you a video. Okay, this is a garden hose, a flexible tube. Okay, so when you increase the flow velocity, the tube becomes unstable. Okay, watch it once more. When flow velocity is small, then the water will just flow out of the tube. Okay? When you increase the flow velocity, you have instability. The pipe becomes vibrating. Okay, so we have this characteristic equation, and by solving the equation, we can find the roots. Okay, depending on the value of the roots, we have different solutions. Okay, so now the roots depend on the loading parameter. It depends on mu. In the case of the pipe, it could be a load P or flow velocity U. Okay, so just think of mu as something related to the loading or related to the flow velocity. Okay, so suppose when the load parameter is 0, you have a pair of complex roots, then the solution is like this. Okay? If we have two complex roots, plus, minus, I omega I. Okay, now when we increase the flow velocity, when we increase the load parameter mu, these roots will change. Okay, so suppose when mu increases, omega 1 decrease. Okay, decrease. So for example, you have plus minus I1, then it becomes plus minus I 0.1, I 0.01, and then plus minus I 0. So that means we have 0 and 0. So it changes from a pair of purely imaginary roots to two double roots, to 0 roots. Okay, so if that's the case, then we would have this. Okay, so when mu is equal to mu critical, we have alpha 1, 0, and omega 1, 0. Suppose when mu is larger than mu critical, then alpha 1 becomes positive. Okay, so there's another thing. So you have 0, and it becomes 0.01, and the other becomes negative 0.01. Okay, so it changes now because of this root. You will have a solution of this form. Okay, so for this case, Q1T is C0 plus C1T. If we have plus minus alpha 1, then Q1T becomes Q1 hat E alpha 1T plus Q2 hat E minus alpha 1T. Okay, this will decay exponentially. This will increase exponentially. This increase linearly. Okay, so when mu is less than mu critical, we have oscillatory solution. We have this solution. When mu is larger than a critical value, then the solution will increase exponentially. Okay, so this is a divergence. Divergence also means buckling in this case. Okay, so that's one case. This is the case when we have divergence or buckling. That means originally we have a pair of complex, a pair of purely imaginary roots. When we increase the load parameter, we will have a positive real root. Because we have a positive real root, the solution will grow exponentially. Okay? So the system changes from this oscillatory behavior to exponential growth. Okay, so this is unstable. This system is stable. Here the system is unstable. Okay, I remember earlier when we studied multiple degrees of freedom system, I got a question. Some people asked me whether omega 1 whether this would be the same. Okay, so for conservative system, we always have distinct values and corresponds to purely imaginary roots. But for a non-conservative system, because of the loading parameter, the roots will change with a mu. Okay, so when mu is larger than a critical value, the roots will change from purely imaginary to a pair of real roots. Okay, one of them is positive, therefore you have exponential growth of the solution. Okay, in another case, we have coupled flutter. Okay, flutter is 颤动. Okay, so similar to the first case, originally we have mu equal to 0, and we have a pair of imaginary roots. Okay, now when mu increases, this increase and this decrease. Okay, so for example, you have I1, say I 0.5, I 0.1. Okay, so when mu increases, it becomes 0.4, 0.2, and then I 0.3, I 0.3. Okay, so they become the same. When you have the same, then you would have I 0.3 and I 0.3. Okay, so now because you have double root, we have A plus BT and C plus BT. Okay? It is still oscillatory, but the amplitude grows linearly. Okay? So we have still its oscillation, but the amplitude grows linearly. Okay, now since we need 2 modes, okay, this is called a coupled mode flutter. You have 2 modes. Originally they are separate, and when mu increases, they become the same, so they become coupled. So that's called a coupled mode flutter. Okay, so originally we have oscillation, and then it becomes unstable. The amplitude grows linearly. Okay, so this involves 2 modes. And third case is called single mode flutter. So we only need 1 mode. Okay, so originally when mu is 0, we have this. Okay, so we have a pair of roots, say 0.5 plus minus I1. And when mu increases, a negative 0.5 plus minus I1. So when mu increases, it becomes minus 0.4 plus minus I something, and then becomes 0.1 plus minus I something, and finally it becomes 0.01 or I something. Okay, now because the real part originally it's negative. Okay, originally it's negative. Then it becomes positive. Okay, so the solution changes from exponentially decaying solution to exponentially growing solution. Okay, so because the real part changes from negative to positive. Okay, then we have the solution grows exponentially. Okay, and because we only need one mode, this is called single mode flutter or Hopf bifurcation. And Hopf is the name of a person, and the bifurcation means 分叉. Okay, so it changes from exponentially decaying to exponentially growing solution. Okay? Now there are some very strange phenomena for non-conservative system. And first, let's look at the effect of damping. And it has been proved by Kelvin that damping has a stabilizing effect for conservative system. Okay, so far we have studied the conservative system. We know that when we increase damping, we can reduce the response. Okay, however, for non-conservative system, damping can have a destabilizing effect. The damping may not be good. For conservative system, damping is always good. It reduces the response. For non-conservative system, damping may not be good. It will increase the response. Okay, so we continue with our example. Here we add two dampers. Okay, so we add two dampers. We can set up the equations of motion as before, and then we look for a solution of this form, and then we end up with a system of two homogeneous algebraic equations. And to find the non-trivial solution, the determinant of the coefficient matrix must be 0. Okay, we have this equation. Okay, A0, A1, A2, A3 are given by this, and we can do a numerical study. Suppose D1, the damping coefficients, okay, damping coefficients D1 and D2 is 1%, okay, 0.01. When P is 0, there are two pairs of complex roots, always negative real parts. When we increase P, the load, one pair of complex roots cross the imaginary axis, leading to positive real part. Okay, the resultant instability is single mode flutter, because we only have one mode. And at the point of crossing, this pair of complex roots become purely imaginary, and the critical value is 9.7. Okay, so let's look at the change of roots. And this is the real part. And this is the imaginary part. Okay, so we have 4 roots, right? We have polynomial equation of degree 4. So we have 4 roots. So when p is 0, we have this root and this root. So they are a pair. And this root and this root. Okay? And both pairs have a negative real part. And both are complex. Okay, so now if you increase a value p, when p is 0, p is 8. 8 is the next point. Okay, so when we increase to 8, okay, so it changed to this point. Okay, so the red dot changes to the blue dot, and 8 is here. Okay, so this pair goes this way, and this pair goes the other way. Okay, so now when p is 9.727, it crosses the vertical axis. So here the real part becomes 0. When p is larger than p critical, so for example 16, the roots are here. Okay, they have a positive real part, and 16 for the other pair are here. So this pair still have a negative real part, but this pair have positive real part. So this mode, this is one mode. This is another mode. Okay, so this mode becomes unstable. And therefore, the critical value here is this much, 9.72715. Okay? Now let's look at the case to compare. We consider the case when there's no damping. When there's no damping, what we have here is you can solve the roots. Okay, so we have 0 here, 0, and this, and this. Okay, so when P increases, this drops to here, and this drops to here. Okay? The red one increase to here. here. Okay, so when P is 17, this goes this way, and the other one the blue goes this way. Okay, so basically we have plus minus I omega 1 plus I minus I omega 2, and then when P is larger than P critical, the roots become alpha 1 plus minus half I omega 1. Alpha 1 is positive. Alpha 2 plus minus I omega 2. Alpha 2 is negative. Okay, so this is unstable because we have E alpha 1t A cosine omega 1t plus B sine omega 1t. Okay, so this term becomes unstable. Now from here you can see the critical value is 17 without damping. Okay, so without damping, the critical value is 17. With damping, the critical value is 9.727. Okay, P equal to 9.72715 for the damped case is smaller than 17 for the undamped case. Okay, so that means damping does not help. When we increase damping, we destabilize the system. Okay, so I don't know if you know the word destabilize. Stable means 稳定. If you add a D, that means make it unstable. Okay, so D means make unstable. However, for this non-conservative system, damping is not always destabilizing. For all combinations of parameters. For example, if you change different kappa and m, the critical value may change. Okay, so for non-conservative system, it is safe practice to neglect small damping in analysis and design. However, for non-conservative system, even a small damping may lead to a significant drop in the load that the structure is able to carry. So we have to be very, very careful when we are with non-conservative system. Damping may lead to destabilizing the system. Okay, so it's important to remember this. If you don't remember anything, today we studied conservative system and a non-conservative system. Non-conservative system is a system in which not all forces are conservative. Okay? And damping will have destabilizing effect. And now let's look at constraints. I'll give you a simple example to think. Okay, so first we studied this, and it has an oil buckling load. Now we add a support. Okay, so it's clamped at one end and pinned at the other end. Which one is larger? PE1 larger than PE2 or PE1 less than PE2? Obviously, we have these. So when we add a constraint, extra constraint, we increase the stiffness of the system. It's a conservative system, okay? So we increase the buckling load. And this is a conservative system. And it's always the case. Now, if it's a non-conservative system, for example, we have a follower force. The force is not vertical, but it follows the deformation of the column. Okay, so we add an extra support at C. Originally we have this. Okay, so we add extra support here. And let's look at the stability. Okay, the structure, because we have extra support, we only need one generalized Q1. Okay, so you set up the equation. It's given by this, and we rewrite. Okay, so you have the stiffness term given by this. Okay, so by adding an extra support, the system reduces from a 2 degrees of freedom system to a single degree of freedom system. Okay, so now a buckling type instability occurs when the natural frequency is reduced to 0. Okay, let me explain this a bit more. If you have Q double dot plus say K, Q equal to 0. If K is positive, the two roots are plus minus I omega. And the solution is A cosine omega t plus B sine omega t. Okay, so now if K reduces, when K becomes 0, then lambda becomes 0 and 0. Then Q is C0 plus C1t. Okay, so a divergence or buckling type instability occurs when the natural frequency is reduced to 0, when the load P increases. Okay, so the yellow term becomes 0, and you can find the critical load. Okay? So as a numerical example, okay, and Professor Tan asked a question. Please explain static instability and dynamic instability. Okay, static buckling. This is a static load. So when P is equal to P Euler buckling, we have buckling. Okay, dynamic buckling means you have the load. It's not a constant, but a function of P. Okay, and it can be deterministic. And the 确定性力 can be harmonic, sine function, cosine function, or periodic. And it can be stochastic or random. Okay, so we will look at more examples of dynamic buckling, dynamic instability in the next hour. Okay, so this is what happens. Lambda are the roots. Lambda are the roots of the characteristic equation, 特征方程的解. Okay, so it depends on the system. And if you have a non-conservative system, and when you increase the loading parameter, you may have different roots. Okay, it's not important to look at the specific value of the roots, but the type of roots. Okay, so for example, purely imaginary roots, complex roots, and when you have complex roots, it's important to look at the real part, whether it's positive or negative. When it's positive, it grows exponentially. When it's negative, it decays exponentially. Okay, and then you have simply alpha. then that's e to the alpha t, alpha positive, or it decays, e to the alpha t, alpha negative. And if you have double root, then we have C0 plus C1t. Okay, so the solution is straight line. Okay, now if you have C0 plus C1t sine omega t plus D0 plus D1t cosine omega t, then the solution is this. Okay, so that's linear. Okay, so it's important to look at the roots of the characteristic equation, 特征方程, and then study the behavior of the system. Okay, obviously, this is the case we studied before, resonance, 共振. Okay, and then in a moment we will look at dynamic stability when the loading appears in the parameter. Okay, so when we have extra support, the critical load is 2.5. Before, without the support, okay, for this structure it's 2.5. For this structure, without the support, the critical load is none. Okay, it implies that the additional constraint, additional support, decreases the critical load of the structure. So this example illustrates that for a structure with follower force or non-conservative system, it is uncertain whether additional constraints would increase or decrease the critical loads that the structure can carry. Okay, so we introduced the non-conservative system. We don't have enough time to go through the details. Look at more examples. But example is buckling with follower force, and you can think about the pipes conveying fluids, okay, or flow-induced vibration. These are all under non-conservative systems. For non-conservative systems, damping may be destabilizing, and additional constraints may also destabilizing the system. Okay, so it's very different from what we have learned so far for conservative system. Okay, we take a short break because next I have a presentation. I don't know how much time we have. Okay, so let's take a 5 minutes break. Now it's 8:46. Please come back. 9:46. Please come back at 9:51. 9:51. Okay, let's continue. And now I give you a brief introduction on dynamic stability of structures. And first we will talk about what's dynamic stability. And we will look at parametric resonance. Parametric resonance, 参数共振. And we will look at nonlinear systems under harmonic loading, 非线性系统. And then some conclusions and remarks. Okay, so first we review static stability. 汤老师，
这样是 OK。
有问题吗？
对，就是我还想请教一下，就是这个 static stability 和 dynamic stability， 它们区别除了这个荷载，刚才你讲荷载是动力的之外，是不是还有把这个质量和惯性力考虑进去？因为我们过去做静态失稳分析，好像没有考虑过质量这个因素。
没有质量，对，这没有质量。行，我们讲完这个再问好不好？因为我这里复习一下那个静态失稳和那个动力失稳。
好的，太好了。
Okay, first let's review static stability. And it's a buckling of a column under actual compressive load. Okay, so here we have a column. It's a simply supported column, or it's supported by a pin and a roller, and it's under a static load P. When the actual load equals one of the Euler buckling loads, the straight configuration becomes unstable. The first Euler buckling load, okay, so the length of the column is L, cross-sectional area A, and the flexural rigidity EI. When P1 is equal to EI, pi over L squared, we have the first Euler buckling load. Okay, so the column will buckle in the first mode, and the shape is half of a sine. And when the load P is equal to the second Euler buckling load, the column will buckle in the second mode, and the mode shape is a full sine. And when the buckling load is equal to the third buckling load, it will buckle in the third mode, and we have 1.5 sine. Okay, so that's what we studied in mechanics on buckling. Now, what's the behavior of the structure when it is subject to dynamic loading? Okay, so instead of a constant load, we have a dynamic load. It changes with time t. And this load can be a harmonic load, a sine function, cosine function, or a periodic load. It can also be a random load. Now, what happens if the load is not a constant static load, but changes with time t? Okay, so to do this, we first review what we studied in Chapter 4 on vibration of continuous beams. Okay, so here we have a simply supported beam under transverse load. Okay, so the load is perpendicular to the actual axis of the beam, and the load intensity is Pxt, and the equation of motion is given by this. If we only consider the first mode, and we consider the load to be sinusoidally distributed, So that means the shape of the load is half of a sine. And okay, so that gives us the shape of the load. And P0t gives us the amplitude. So the load will always change in this shape. Okay, so it changes in this shape, but different amplitude. And we consider the first mode, and so the transverse displacement V xt can be expressed as qt times the shape. And since we consider only the first mode, the equation of motion becomes this. It's a single degree of freedom system. Okay? And the load, pyramid P0, appears on the right-hand side. It's very important. Okay? So in this case, the load appears on the right-hand side. Loading is on the right-hand side, and the structure is equivalent to a mass spring damper system under dynamic load. That's what we studied in Chapter 2, a single degree of freedom system under externally applied load. And if we consider harmonic excitation, this is the response. And if we don't consider the dynamic effect, only the static effect, we have this. So you find the static deflection given by this expression. Okay, we can define the dynamic magnification factor. It is the maximum dynamic response over the static deflection. Okay, so the maximum dynamic response is given by this. And then we have the dynamic magnification factor. R is the frequency ratio. It is the excitation frequency, big omega, divided by omega 0. Omega 0 is the natural frequency of the system. Okay, so when the frequency ratio is equal to 1, or when the excitation frequency is equal to the natural frequency of the system, we have resonance. Okay? And at the resonance, if damping is 0, excitation frequency is the same as the natural frequency. We can find the response. There is an extra t here in the solution. Okay? So that means the response of the system increases linearly with time. Okay, so if you excite the beam, when the natural frequency is the same as the excitation frequency, the response will increase linearly with time. Okay, so excitation frequency is the same as natural frequency of the system. This is called mean resonance. Okay, now let's look at a slightly different situation. Before, the load is transverse. Now we have actual load. Okay, so the loading is actual load, not a transverse load. So when we set up the equation of motion, Pt appears here. If you consider only the first mode as before, and we consider dynamic loading as a sinusoidal force. So PT is equal to P0 cosine nu t. Okay, nu is the excitation frequency. So P is P0 cosine nu t. And so as Professor Tang mentioned before, when we study static buckling, we only need A, E, I, and L. When we study dynamics, we need to consider the mass for inertial force. And we also consider damping if there's damping in the system. Okay? So for statics, we don't have the inertial force and the damping force. This is the same as what we studied before, mx double dot plus cx dot plus kx equal to pt. And the inertial force and the damping force are dynamic forces. So when we study dynamics, we need to consider mass, the inertial force, and damping. Okay? For statics, we only have this term. And if you go back, I think this probably is clear. Okay, so for dynamics, we need to consider this whole equation. If we consider only statics, we only have the elastic force and the amplitude of the force. There's no variation in the force. Okay, so this part is statics. And for dynamics, we have the inertial force and the damping force. And the load changes with time t. Okay, so now if we consider only the first mode, and we consider the load as the sinusoidal load, it changes with time in the form of a cosine function. Okay, so then we end up with this equation of motion. And there's something very special here. The forcing term is not on the right-hand side, but it's a coefficient of qt. Okay, so excitation becomes a coefficient or a parameter of the system. Okay, so it is parametrically excited.这是参数机理。Okay, the forcing does not appear on the right-hand side, but appear as a parameter of the system. Okay, and then we have this cubic nonlinear term. It's when we consider the nonlinear behavior of the system. So this is parametrically excited, and this gives us nonlinear. Okay, and then we define the parameters as before. Zeta is the damping coefficient. Omega 0 is the natural frequency of the system. Nu is the amplitude. Mu is the amplitude. Nu is the excitation frequency. And we introduce a small parameter epsilon. Okay, because we have to use an approximate method to study this system. Okay, so we introduce a small parameter 小参数 for analysis later. Okay, and so when the case that we have sinusoid loading, if we only consider linear first, okay, we drop the nonlinear term. For linear system, the loading appears in the Q term. And mathematically, this is called a Matthew equation. And Matthew is a mathematician. Okay, so this equation is named after Matthew. Okay, when the system is undamped, that's the equation. And I will go through the analysis very fast. We just need to understand the behavior of the system. Okay. We apply a time scaling, so time nu t, we call it a new time tau, and we define the frequency as nu zero. Nu zero is a reference frequency, and delta is called a detuning parameter. Okay, so when we define this, that means nu has a central frequency nu zero. Okay, and then it changes in a band. So this is epsilon delta, and this is minus epsilon delta. Okay, so all delta can be positive and negative. So that means the frequency changes in a band with central frequency nu zero. 中心频率，或者是叫参考频率。Okay, and the frequency will change in a band of with epsilon delta. Okay, so now with this transformation, we can rewrite the equation in this form. Okay, so now the time is tau. And we have an epsilon, move the term, small term, to the right-hand side. Apply the method of variation of parameters. And if you forgot this, and you review what we studied in differential equations. Okay, so I will just explain the results for you. Okay, so we have A tau, this is the amplitude, and the phi tau is the phase angle. So in terms of A and phi, we have this equation. Okay, so originally the equation is in terms of Q and Q prime. Okay, Q and Q prime. You make a transformation to A and phi. Okay, so in terms of A and phi, we have these equations. Epsilon is small, When epsilon is small, A prime, the derivative, and phi prime are small. The derivative means the rate of change. With time tau. Okay, so the rate of change with time tau is small. That means A and tau change slowly with time tau. Okay, so you can see Q is the black curve. A is the amplitude. Okay, A is the amplitude or the envelope. Okay, so A is the envelope of the response. You can see Q changes very fast, right? Q changes very fast, but the amplitude A changes slowly. Okay, so that's very important in one period. In one period, Q varies very fast, but A changes very slowly. Okay? Then we apply a method called method of average. And that means we take an integral over a period t, okay, over period t, and divided by t, and take the limit t approaches infinity, where the integration is performed over explicitly appearing. Okay, this is implicit tau. Okay, this is implicit. Implicit means 引字。I don't know even how to write Chinese. Sorry. Here, this is explicit. Okay, explicit. So this tau is explicit. So we need to deal with cosine tau and cosine tau. A tau and phi tau are explicit. So these are explicit tau. Okay, so make sure you understand explicit and implicit. Okay, so now we apply the averaging, and when tau appears implicitly, we replace A and phi by A bar and phi bar. Okay, and then we evaluate the explicit tau term. Okay, explicit tau term. The effect of averaging operator is to smooth out the higher order or higher frequency variations in A tau and phi tau, and to retain only the first order variation, first order approximation. Okay, this is a very nice diagram. The dark line is the true amplitude, A tau. Okay, and the red dashed line is the average. So you can see for the black line, you have some higher order variation. The red line is very smooth, okay? It only keeps the first order variation. And the Q changes very fast, okay? But A does not change fast, it changes slowly. Okay, so when we go through this, we end up with the equation. Now, when kappa is not equal to half, when kappa is not equal to half, or mu 0 is not equal to 2 omega 0, okay, this term and this term is not 0. Therefore, we have sine something tau, cosine something tau. Okay? So, sine, cosine, when you average over a period, it's a 0. Okay? So, when kappa is not equal to half, when you average over one period, it becomes 0. Okay, so then A prime, this term becomes 0, and cosine becomes 1. Okay, so becomes 0. So we have 0 and 0. Okay, so A bar prime is 0. We only have this term left. Sorry, this term is 0. This term is 0. And this term is 0, so we only have this term left. 0. So now A bar is a constant, and phi is, when you integrate, is epsilon kappa delta tau plus a constant. So the solution is a cosine function. And this solution is the same as the system without forcing. Okay, so that means the forcing term has no effect. Okay, so if nu is not equal to 2 omega 0, the parametric forcing function has no effect on the system in the first order approximation. Now, if kappa is equal to half, then this term becomes 0. Okay, so we have a constant sine 2 phi bar and cosine 2 phi bar. Okay, so you have this sine 2 phi bar and cosine 2 phi bar. Okay, now we can convert to rectangular coordinates, x as a bar cosine phi, y as a bar sine phi, and then you get this system. This is a system of linear ordinary differential equations with constant coefficients. We look for a solution. We separate a tau, that's an exponential term here, and then we end up with this. And that's a system of linear algebraic equations to have non-trivial or non-zero solutions for x hat, y hat. The determinant of the coefficient matrix must be 0. Okay, then we have this. Okay, then we have the roots. Okay, this is similar to the lambda that we used before. Okay, so this is a characteristic equation. Okay, and the roots are like this. Now, if mu squared over 4 minus delta squared if this term is negative, okay, if this is negative, then square root of negative is purely imaginary. Okay, so then we have a pair of imaginary roots. The solutions are periodic functions, so we have periodic solutions. Now, if this term is 0, if this is 0, then we have 2 zeros. Okay, then the roots are 2 zeros. And the solution is like this. Okay, so the solution will grow linearly in time tau. Now, if it's positive, if this is positive, then you have a positive root and a negative real root. Okay, so let's say row 1 is positive. This term will grow exponentially in time tau. Okay, so if we sketch this, the instability region is this. Okay, so that means nu over 2 omega 0. Okay, that's the frequency ratio. We sketch here nu over 2 omega 0. And if it's in this yellow region, V-shaped region, then the system is unstable. The solution grows exponentially in time tau. Okay, now if you have damping, then the stability region is like this. Okay, so no damping. If there's damping, the region is this shape. Okay, so there's a minimum value 2 zeta. So that means the amplitude of excitation must be larger than 2 zeta in order to excite the system. Okay, now let's do a simulation. Okay, so we have damping 0.1, the amplitude is 1, and the natural frequency of the system is omega 0 equal to 1. If nu is 1.8, and the frequency ratio is nu over 2 omega 0. Okay, and the point is here. So it's outside of the unstable region. You can see the solution decrease exponentially to 0. Okay, so when the excitation frequency is not in the vicinity of twice of the natural frequency of the system is stable. The response will decay to 0 exponentially. In the stable region, the response of the system decays exponentially when there's damping. Okay, maybe I put all this out. Okay, now for the same parameter, if the frequency is 2, okay, so nu, the natural frequency is 1, so 2 omega 0 is 2. and nu is 2. So the excitation frequency is equal to twice the natural frequency of the system. So when the excitation frequency is in the vicinity of twice of the natural frequency of the system is unstable. Okay, so that's this point. It's inside this region. In the unstable region, the response of the system grows exponentially. Okay, you can see it clearly. The response grows exponentially, even when there is damping. Okay, so as comparison to the mean resonance. Mean resonance is when the excitation appears on the right-hand side of the equation of motion. Resonance occurs when there's no damping, when the excitation frequency is the same as the natural frequency of the system. When resonance occurs, the response grows linearly. Okay, grows linearly with time t. For parametrically excited system, the excitation appears as a parameter, okay, part of a coefficient. And resonance will occur not at a frequency, but in a band of frequency. Okay, so in a band of frequency. Not a single frequency, but in a band. As long as it's in this band, we will have resonance. And even when there is damping, the response will also grow exponentially. Okay, so that's very important. Even when there's damping, the response will still grow exponentially. Okay, so that's the difference. Resonance and mean resonance. This is a simple example. You may have played a swing. Okay, so obviously, when you are a kid, you have this. Okay, you can have somebody pushes you. You can have your mother or father pushes you, and then you will be able to swing. When this is externally applied load, the push appears on the right-hand side. Okay, the push appears on the right-hand side. And then the way you push is, you start from here, you go to this side, and come back. Okay, so you push, and push. Okay, so when you come back, you are being pushed. And this is one period. Okay, and the excitation frequency is the same as the frequency of the system. Okay, now if there's nobody to push you, you can push yourself. You can excite the swing yourself. What you do is you stand up at this extreme position, and then you squat down. 在这个位置你站起来 ，at this position you squat down， 你蹲下来 ，and then you stand up. Okay, so you can see for the swing, it's here. You go to this position, come back, come here, come back. Okay, so that's one period. And it corresponds to squat, standing, squat, standing, and squatting. Okay, so when you do this, squatting to standing, squatting, that's one period for you, right? And for the swing,